Good morning, Professor.
I got it.
Good morning, Professor.
You can hear me, right?
Yeah, yeah.
Okay. So I guess you must be also in your dormitory.
Yes, Professor.
I guess you must be also in your dormitory.
Yeah.
Yeah. Yeah, there will be a
Because of
box.
fourth floor working.
Yes. Which makes you kind of inevitable vacation today.
No, Professor, that we do not go to the lab, but we have a class.
Yeah, but you have only one class today, right?
No, Professor. I have two class.
Two classes.
Another class, Professor Kintai.
Professor Taeyim?
Kintai, yeah.
Oh, okay. So online is good sometimes.
Yeah.
Maybe not good for students, but okay. So I guess you are also presenting today.
Yeah.
So are you ready?
Yes, Professor, I will.
Okay. I don't know whether two study students, they know whether we have a class or not. I hope they did not think that class. Oh, okay, she's coming. Hi, Manar.
Hello, Professor.
Good to see you. I'm in my older son's room because you know that we cannot go to the office today. So that's why you see a little bit different background today. Hi, Jihoon. Long time no see. I thought you dropped the class.
Morning, Professor.
Okay. Jihoon, you must be also in your dormitory. You're not? I don't hear anything from you, Jihoon.
Can you hear?
Yeah, now I can hear.
Yeah, I am now at home.
Okay, you're home. But it seems like you're always carrying on your headphone.
Yeah, I have headphone in my home too.
Okay. Hi, Nur. Good morning.
Good morning, Professor.
Yeah, you look still sleepy.
Yeah, sleepy.
Okay. If you want to wake up, just let me know so that you can lead the class.
Okay.
I think that both Manar and Nur, you have experience for teaching, right?
Yes.
Mm.
Yeah.
So you want to teach a class? No?
No.
Okay, since I don't know, Je우 mentioned that he visits his hometown for having his kind of some physical checkup. I don't know whether he can join or not, but he told me like he cannot today. So we can just start. So Garlic, you can share. I will start to make everybody can share. So that you can share now for your materials. And then you can start. Sorry, can I hear?
Okay.
Good. Yeah, maybe it's just better to place your microphone close to your mouth. Okay.
Good morning, hello everyone. Today I want to talk about laser in urology. So first I want to tell some different types of laser in urology. One is carbon dioxide laser. It is the one of the best laser precisely cutting tissue, and argon ion laser and ND laser. It used for coagulation of the highly vascularized tumors of malformation. And ND laser is prepared to the coagulate large tissue volume due to the high penetration depth. And another is tube switch and diag laser. The photodisruptive mode have become a standard tool in lithography, and dye laser not been investigated in photodynamic therapy. After the first fiber optic endoscopy developed NAS in 1973 and Stellar 1976, they performed the initial experiment studies in argon ion laser urology. And scheme of male urinary tract, and it consists of 6 parts: external genital, lower urinary tract, urethra, bladder, kidney, prostate, and upper urinary tract. External genital, condylomata equaminata. This is the most malformation of the external genital, and benign warts must be treated as early as possible. It tends to be a infection and degenerating. Circumcision and application post-Watson efficacy to suspected area, and they can be convoluted with either NDAG or laser, and their rate of recurrence is less than 10%. Hemogenius of the external genital, it should be treated with a NDAG laser because of its higher penetration depth. Carcinoma of external genitalia, it is the one of the best treated with the NDAG laser at the early stage of reduce the risk of the partial amputation, and it use power for 40 watt and focal spot size of 600 micrometer. And another one is lower urinary tract, and here here one of this stenosis. It's a frequent disease in lower urinary tract. It's induced by inflammation, tumor growth, and unknown origins. Urothrotomy by endoscopic control is usually performed. Stenotic material is removed with a cold scalpel, and restenosis often occur due to the scarring of tissue. In 1980, Rotag used a argon ion laser to recanalize the urethral stenosis. And Hoyag laser treatment is considerable alternative to the mechanical urothrotomy in virgin stenosis as well as restenosis. And it used 30 pulses with energy 370 millijoule, and their approximate duration is 1 millisecond. And another one of the part is bladder. Tumor of the bladder is very difficult to since tumor tends to recur after therapy, and it easily breaks through the bladder wall. Frank compared carbon dioxide, NDAG, and argon laser on bladder tissue, and NDAG laser proved the best suited and convoluting bladder tumors. Argon ion laser are applicable in superficial bladder tumor. And Hofstadter in 1980 he suggested the superiority of laser method over a TUR, that is the one of the technique transurethral resection, and their recurrence limited to 1.5, and another one is 40 to 60. And photodynamic therapy is considered is a useful supplement to other techniques, and it's enable to resection of tumors which are not visible. Laser induced fluorescence and treatment of cancer is one of the key advantages of using photodynamic therapy. Lithotripsy of a urinary calculi. It's often based on ultrasound technique, and it not only calculi are equally indicated by the external therapy. Calculi are stuck inside the ureter are in extremely inconvenient location. Mulvaney and Beck in 1968 they performed the first experiment of the laser lithotripsy by using the ruby laser, and this technique associated with severe thermal side effects. Pulse dye laser were investigated by the Watson in 1987. Their experiment have a decrease in pulse duration. Additional complication arose the concerning induced damage of the fiber. And nowadays, dye laser and DX laser is very preferable used in lithotripsy of the urinary calculi inside the ureter. And Hofstadter in 98 he performed an experiment, and his pulse energy was 50 to 200 millijoule, and pulse duration between 10 nanosecond to 1 microsecond. Diameter of the optical fiber varies between 200 micrometer to and 600 micrometer. And prostate is very sensitive organ in embrace of the urethra. A common disease is benign prostatic hyperplasia. It's called in carcinoma, and which can cause a problem of discharge of urine. And Boarin in 1979 were the first to investigate the effect of NDX laser radiation on tumor on the prostate. Sander and Beesland and Standard pointed out the extreme importance temperature monitoring of the adjacent rectum. BPH treatment of BPH uses two techniques. One is the tulip transurethral ultrasound guided laser induced prostatectomy. And here Ross and Arts in 1991 and Johnson in 1992 proposed the tulip idea. McCullough in 1993 published the clinical radar. The main element of tulip is position 90-degree prism inside the urethra by the ultrasound control, and precision in aiming at the target is strongly enhanced. And another treatment of BFH is laser induced interstitial thermotherapy. It's called LITT. MC Nicholas in 1991 and Masseter in 1992 published their initial experiment results of LITT. And laser power was 1 to 5 watt and coagulation volume with diameter of up to 40 millimeter. And their urinary follow rate increased 6.6 milliliter per second to 15.2 milliliter per second, and urinary volume decreased from 206 milliliter to 38 milliliter, and their weight of the prostate dropped 63 gram to 44 gram during the same period. And this data based on mean value of the obtained 15 patients, and from this result it can be concluded that the LITT is a excellent therapy of BPH. Thank you.
It's amazing to me that you don't really have kind of any photos or figures to explain about each therapy, and then just using the basically words to describe them more. I don't know how other students kind of understood about your material, but I think that the material itself needs to be updated. So Garly, just, I mean, when you are talking about like tulip and those things, it's much hard to imagine what are those without having any video or the photos or kind of illustrations. And if you just kind of describe them about by using the word it only, then it's hard to understand. So I suggest you to update your materials, to update your slides, so that others can understand better. And then I believe that the slides that I shared with all of you in the what's the name? In the portal, if you go to that, and then I actually shared the previous students' slide, and then they have quite many photos already in there. And then the reason why I was sharing the previous student slide with all of you is that based on that slide, I wanted you to improve the slide, so make it better. But this one, I don't really feel like this has been better than previous slides. So I really strongly recommend you to update your slides and then just do one more time. I'm giving you a second chance not to get low score, okay? Because you know that there is no midterm exam, so that the only your grades will be purely based on your attendance and also the presentation and final exam. So if you are not having good score from your presentation, then your grade can be highly affected by that. So as I gave the second chance to actually Jihoon before, you also need to upgrade your slide and then giving more intuition about that. And then when you are using your presentations, I don't know. I mean, you have to prepare more to make other students to understand everything about your slide. So whatever written on your slide needs to be explainable. So I guess, I mean, other students did not ask any question today, but if they are asking questions, then you need to be ready to answer. So regarding that, I actually forgot to add other students whether you have any questions to his slide or to his presentation. No question? Was it just kind of too quick? No response. So Garlic, congratulations, you got a second chance. So update your slide and then let's do your presentation one more time on next Thursday. Okay. Right. So let's go back to the previous slide. So Manar, what is the plasma?
One component in the blood.
One component in the
In the blood. Mhm.
Okay. Yeah, I mean that's plasma. But what I meant here was the plasma state. So there is a gas, liquid, and the solid. And then the plasma is also called as a forced state.
Mm.
And then, so what plasma is that?
I have no idea.
Oh, I think I mentioned during the last class. Anybody, I mean, did you all watch the video? Ji-hoon and then Manar and Nur, you didn't? Oh, Garlic, did you watch the video? No? Ah, I mean, then why do I have to record and then upload on the YouTube if nobody watch? Okay, so Ji-hoon, you said you watched. So what is the plasma?
I don't exactly remember, but the particle was blow up, and then it's gonna be plasma. Maybe I understand like this.
Particle was blow up and then?
And then the energy
Uh-huh.
was radiated. That is the plasma, right?
I didn't hear the last part. The energy was.
Energy was radiated,
Mm-hmm.
and then that's gonna be the plasma.
Okay, not exactly. But Simpson Nur, you know about the plasma. No? No?
I know that it is one of the interactions between the plasma and the body, like the photodynamic therapy and like we have thermal ablation, and this is a plasma induced ablation. It is one type of the laser therapy, but I don't know exactly about plasma.
So it's opposite to the Manar case. So when I asked Manar for what is plasma, and then she said it's one component of the blood. When I started my study in the United States, the first class was artificial organs class. And then in that class, the professor was mentioning about the plasma. And then I actually didn't know what is the plasma there. So because the plasma that I knew was not the plasma that one of the component in the blood. I even didn't know that that is called as a plasma in the blood. So the plasma that I knew was because my master's background is on the material science. So that I have been using the kind of system called as a spotter, a radio frequency spotter. And that is basically making the deposition of the very thin film on some materials by using the plasma. So the plasma that I knew is basically same here, same thing that I'm talking about today here. So plasma is basically state something similar to the gas. However, the difference is that in the gas state, atoms are in a neutral state. However, in the plasma, they are breakdown into the positive and negative ions. So basically, when the neutral atom is losing the electron, and then they are becoming positive ion plus some free electron. So ionized state is basically plasma. And that's the basically the difference between plasma and gas state. So that plasma was the one that I knew about plasma, and then in that class, he was mentioning about the blood component of the plasma, but I was having no idea about what is plasma in the blood. So I asked question to him and then say, what is plasma? Like that. So plasma here is meaning the kind of mixture of the neutral atom and then the ionized atom and a free electron. Those are the plasma state. And then you can easily imagine that when you are making the atom, the neutral atom, to be ionized, and then those atoms can be basically dissociated into two components. One is the positive ion, and then one is the negative electron. And then that process itself is making the component of the tissue or molecules or atoms of the tissue to be basically ablated. So plasma-induced ablation means that you are generating plasma by using the laser energy. And then when the plasma is formed in the tissue, then that part is going to be basically ablated so that we can remove the tissue. So that is the plasma-induced ablation. So here, since only Ji-hoon watched the video, I need to re-explain everything here. So as you can see in this photo, this is showing the tooth. And then, but here you can see there is a, sorry. There is a, there is a something here, the plasma spark. And then that is, I mean, it's very quick process. So to capture this moment, they have to use the very fast rate, the video or camera. So when the laser is coming into that position, and then they generated plasma, and then you can see the plasma spark comes out on the surface of the tooth. The next slide was mentioning about the optical breakdown. So optical breakdown is having three different forms. One is the plasma formation, and the other one is shock wave generation, and then cavitation. Cavitation here can happen only in the fluid or very, very, very soft tissue. And then this plasma formation is corresponding to about 70% to 99% results from the optical breakdown. And then only 1 to 5% of the energy from the optical breakdown can be shown as a shock wave. And then if the optical breakdown, which is induced by the laser, and if that's happening in the soft tissue or fluid, then 15 to 25% of that energy can be shown as a cavitation. Once the cavitation occurs, if that is close to the boundary between the fluid and then the solid, then jet formation can happen. And then here, those three are going to be discussed in the photo disruption. And then here is going to be mainly focused on plasma-induced ablation. And then either both of them, photodisruption or plasma-induced ablation, is going to cause the tissue ablation. And then I was showing this kind of video to show that when the optical breakdown occurs in the gas, then what happens? And then I don't know whether you can hear the sound. So you can actually see the spark here. And then that is happening when you are focusing your laser beam into very small focal spot and then giving very high density of the energy. Then so-called as the optical breakdown occurs, and then the plasma is one of the form from the optical breakdown. And then since the optical breakdown is generating the plasma, and then when the plasma is happening, that is basically breaking the neutral atom into the positive ion plus free electron. And during the process, there is also light comes out, and also sound is also generated. And you can see kind of bluish, kind of star-like color in the air, and then making that kind of sound. Okay, hi Seung-young, how are you? Doing okay? Can you hear me? No? Okay, I don't know. So examples of the plasma-induced ablation is shown here. So the top one is showing the cornea by using the 30 picosecond and with the 200 microjoule energy. You can see that plasma-induced ablation is causing very clear ablation without giving a damage to the surrounding tissue that much. If we are doing thermal ablation, let's say I'm going to increase. You can see this ablated area is very clean, and then surrounding tissue doesn't really show very specific thermal damage. But if that was done by giving a long pulse of the laser, which can cause the thermal interaction, in that case, you can expect the surrounding actually quite large area can be damaged by hyperthermia or coagulation, or even right next to the ablated area will be carbonized. So those things can happen when the thermal interaction occurs. But in here, plasma-induced ablation seems like having a very nice clean cutting of the cornea. The bottom one is showing the tooth with the 30 picosecond and the 1 millijoule pulse energy. And then it was cutting the one by one surface area on the tooth. So you can see the very clean damage on the tooth here. Okay, Seung-young, now you can hear me?
Yes, Professor.
Okay. So plasma-induced ablation has a threshold. That is because you need to first able to generate plasma by using the laser. And then plasma, as you can imagine, it doesn't really happen easily. Otherwise, it will not be called as a fourth fundamental state. If the plasma can be generated so easy, then actually you can see that kind of in the surrounding, atmosphere. However, it cannot. So when you are using the laser for plasma-induced ablation, the most important parameter is you need to generate plasma. And for the generation of the plasma, the important thing is local electric field strength. So how strong electric fields are occurring in that laser focused volume, that is going to determine the threshold of when optical breakdown happens. So the threshold is basically how strong electric field you have to apply. And then that electric field is making the molecules or atom to be ionized. So the relationship between local power density I in the tissue can be from 1/2 with the epsilon sub 0 multiplied with the C and then E squared. So this local power density I is depending on square of the electric field. So when you have a strong electric field, then it can have a higher power density in the tissue. And then the plasma can occur. So typically, the threshold intensity for the optical breakdown is about 10 to 11 watt per centimeter square when you are using picosecond pulse. The later it will be shown also that when you have a shorter pulse duration time, then the threshold level can be going down. And then when you have a longer pulse duration time, then the threshold level of the intensity is going up. And then that is basically deciding whether plasma-induced ablation versus photo disruption, as you can see in this slide again. Here you can see the plasma-induced ablation is occurring at the a little bit shorter pulse duration, but with a lower power density. For the photo disruption, you can see it happens with a little bit longer pulse duration, but you need to have a high power density. So depending on the pulse duration time you have, you can actually make a plasma-induced ablation with a lower power density, or if you have a longer pulse duration, you need to have a much high power to make the photo disruption. However, here, photo disruption is actually also one part of the optical breakdown. And then to make the optical breakdown, you need to have a very high energy focused in the small tissue volume. But here you can see the overall power density, or even actually energy density. You can see the energy density point, the photo disruption has a higher energy density compared with the plasma-induced ablation. So that means that the photo disruption is having much higher energy compared with the plasma-induced ablation, so that it can actually mechanically damage the tissue when the laser is kind of focused in specific area of the tissue. So the threshold intensity of the optical breakdown is about 10 to 11 watts per centimeter square when you have a picosecond pulse. In that case, the corresponding electric field strength is 10 to 7 voltage per centimeter. So within 1 centimeter, the difference between those 1 centimeter in terms of the voltage is like 10 mega voltage, which is hard to imagine how strong it is. And then that electric field can be comparable to the average of the atomic or intramolecular Coulomb electric field. So you know about the Coulomb electric field. So basically Coulomb force between the two the ions. So when there is a positive and negative, then they are having attractive force, which is the Coulomb force. And then the Coulomb force is increasing when the distance between positive ion and the negative ion is having the separation each other. So when the separation is smaller, then attractive force is increasing dramatically. And this 10 to 7 voltage per centimeter is kind of some level, which is kind of comparable to the Coulomb electric field. So what they mean is that if you are providing higher than that 10 to 7 voltage per centimeter for the electric field, then it can actually break down the attractive force between positive and negative so that those can be separated each other, which is the ionization process. So within very short, a few hundred picoseconds of the pulse duration time, a very large free electron density, typically having 10 to 18 per cube centimeter, can be created in the focal volume of the laser beam. And then plasma generation from this high intense electric field is also called as a dielectric breakdown. And then this is also optical breakdown. And then optical breakdown is emphasizing that the UV, visible, or infrared light are strongly observed by the plasma itself, which is shown in this right side figure. I think that we have a chance to discuss about this, but okay, maybe now. So that I need to briefly explain about this one. So this graph has been shown in the previous lecture for the photoablation. So Seung-Young, for the photoablation, basically by giving a single pulse, you can expect how much of the tissue will be ablated. And then this graph is showing the relationship between energy density as an x-axis and the y-axis is as a ablation depth. So that photoablation we can actually we can predict of how much of the tissue will be basically removed by giving a laser pulse. And that can be in this graph, which part of the graph is showing about that linear relationship between the energy and also ablation depth.
I can really understand your questions, but your question is what is the region of the linear relation?
Yeah, in a simple way, yes.
In the red circle.
That looks also linear. But here actually the reason that I was trying to point out is here. So between this energy density area, the relationship between increase of energy density versus ablation depth is showing very good linear relationship. However, after certain high energy density, which is shown on here, it looks like it is saturated. It doesn't show continued linear relationship, but it is showing saturation. So, Carly, can you imagine why suddenly this is saturated in this high energy density? So we expect that if we are increasing energy density, then we can have a more tissue ablation occurs. However, it doesn't, and then it shows the saturation. Why that will happen? The key point is plasma. Lu, can you imagine why the plasma here is going to make saturation in this graph? Jihun, you watched the video, so you probably know the answer. Not really. Okay, Manar. Okay. Actually, it will be explained in the following slide. So I will show you the following slide. That is because of the plasma is generated. The interesting point is that the plasma itself is absorbing the laser energy. So that if you increase, even if you increase energy density, that cannot be actually shown as an ablation, because at this moment, which can be considered as a threshold intensity for the optical breakdown. So in this energy density, optical breakdown occurs, and then the optical breakdown is basically plasma formation. And the plasma formation is actually observing the succeeding laser, so that the increase of the laser energy cannot be used to remove tissue, but it will be just observed by plasma itself. Since I do not have a pen, but I'm just using the mouse, but let me explain whether it is explainable or not. So when you have tissue at the bottom, and then you can use the laser, and then of course, actually, laser will be also focused. This is the kind of exaggerated figure, but you can imagine here in the center is kind of highly focused region of the laser. And then this optical breakdown is not happening easily, actually, and that it can happen when the laser power or laser energy density is higher than the threshold level. So in this focused region, its density, so that means that the power per area multiply with the time. So within very short time, but in a small volume but high power, then in this region, the plasma can occur. So let's say plasma is shown here. So before plasma is generated, the relationship between ablation depth and then the energy density is showing the linear relationship. But once it is beyond the threshold, so now the plasma has been generated here. And this plasma is actually observing the laser coming into this region. So that increased energy by the laser is going to be actually observed by the plasma, which is generated in this area. So that no more ablation occurs because the energy of the laser is simply observed by this plasma itself. So the Fradin have done some experiment on the salt, sodium chloride. So they put the sodium chloride and then giving a ruby laser pulse, and then looking at the intensity with the time. So the red line for each ABC is showing the threshold for the optical breakdown. So when the optical breakdown can occur, depending on the ABC here. So the top one, A, is showing the increase of intensity with the time, which will be corresponding to the pulse duration. So in this case, that was like about 40 nanoseconds. But here, since all the laser energy was lower than the threshold for the optical breakdown, so that you can actually see all the light is coming out with respect to the pulse duration time. Increase and then coming out. The second one is showing that it starts to increase and then suddenly it went down. That is because in this case, the threshold was reaching at this intensity level here. So once the pulse energy is reaching the threshold, it starts to generate plasma, and then the plasma is absorbing the succeeding laser energy, so that the coming out laser is basically suddenly disappear, and then it doesn't come out. Same thing for the C. In this case, the threshold was a little bit higher, so that you can see the increase of the transmitted laser intensity. However, once that reach the threshold, the plasma observe the laser energy, and the no more succeeding laser will come out in this case. And this figure is explaining about the initiation of the ionization, which is the basically plasma formation. So by using Q-switch laser, it can generate nanosecond pulse. But by using the mode-locked laser, you can have a much shorter pulse duration, either picosecond or femtosecond. By having a long pulse duration compared with the picosecond or femtosecond, nanosecond laser will have a heat generation. And then once the heat is generated, it increases temperature. And once the temperature increases, the high temperature can basically eject electron to the outside. So that is called as a thermionic emission. So with a high temperature, electron can be ejected, and then that is called as a free electron. For the mode-locked laser, you can have a much shorter pulse. In that case, the photon is coming into atom, and then the multiphoton ionization can occur. So multiphoton ionization occurs when multiple photons are coming into the atom, and then the multiple photons is providing high enough energy so that the electron in the atom can be also kicked out from its position and then becoming free electron. And then that neutral atom is now having positive ion. So this free electron is now generated either by using thermionic emission or multiphoton ionization. So electrons are happy. Woo, yeah, I'm free. I can go anywhere. And then if you continue to supply energy by using the laser so that another photon is coming. And the photon is actually giving the energy to the free electron by inverse Bremsstrahlung. So Manar and then Nur, you actually took the medical imaging class last semester. Then I hope you remember about what is the Bremsstrahlung. So Manar, can you tell us about what is the Bremsstrahlung?
When there is an electron that strike an outer it's called inner orbit of the atom. What happened is that one electron is ejected from that orbit and goes lose some of its energy and become another one goes from the higher orbit to the lower orbit of the atom. So there will be an energy. That energy called as Bremsstrahlung energy.
I think that you are talking about the characteristic X-ray radiation. Bremsstrahlung is actually similar to that, but it is happening when very fast moving electron is getting closer to the nucleus, which has a proton, and the proton is positive. So the electron is, let's say, where I can draw. So there is a proton in the center, and then we have an electron, which is negative. So when the electron is coming toward this proton, because of the attractive force between positive and negative, it cannot just simply pass. It will be getting closer to the proton and then changing this direction. And also in this process, the electron is going to be slowed down. So moving very fast, and then because of the attractive force, it changes direction and also slow down. So the slow down means that there is a loss of the kinetic energy, and then the loss of kinetic energy is coming out as a form of the radiation. So here is called as inverse Bremsstrahlung. What they mean is that by having some energy from the radiation, the slow electron is gaining energy and then becoming fast electron. So that's the inverse Bremsstrahlung. So here there is a free electron with some specific kinetic energy. And then when the photon is irradiated into the area, this free electron can actually obtain energy from the photon, and then having the higher kinetic energy, which means that from the slow to the fast. So now the free electron is having fast, which means that high kinetic energy, so that it actually provides enough energy to make another electron to come up from the original atom. So now you have a single free electron becomes extra and then original one here. So 2 free electrons. And the 2 free electron can become 4 free electrons. So 1, 2, 4, 8, 16, 32, 64, 128, and 256 like that. So it is a very rapid increase of the free electron. And that's why it is called as electron avalanche growth. So avalanche is actually presenting the process here, showing the very rapid growth of the number of the free electron. So you can imagine when this is happening, the atoms in this area, in this volume, is going to be ionized, and then plus free electron, which is the plasma state. So now you have a plasma state in this volume by having this high kinetic energy free electron. But here also you can see that to maintain this plasma, you need to have a kind of continued supply of the energy, because if you stop laser, then there will be no more photon, and then this free electron will not have any more supply of the kinetic energy, and then no more this ionization occurs, so that the plasma will be disappear immediately. So initiation of the ionization occurs by 2 mechanisms. One is the thermionic emission. In this case, when the temperature is going to very high, then it releases electron. And then second one is multiphoton ionization. And this one, when you have a coherent absorption, so this is also a key point. What that means is that you need to provide the same energy of the light, so that the photons there are having same energy each other. So that when you have a multiples of the same energy photon is coming, then it provides high enough energy to make electron to be free from its original position. So multiphoton ionization can be achieved only during the high peak intensity in the picosecond or femtosecond laser pulses. So with a high peak intensity, so if we are giving the pulse like that, it will initially, this is the pulse we are giving. However, what's really happening is like that. So during the peak time here, this multiphoton ionization can happen. For the Q-switched laser pulse, which is able to give a nanosecond, it provides a higher plasma energy, and also plasma temperature is much higher compared with the mode-locked laser pulse, which is generating picosecond pulse. So as I mentioned in the previous slide, when you have a longer pulse duration, the threshold of the plasma is also increasing. So compare with the picosecond, when you have a nanosecond pulse, to make the plasma, you need to have a much higher power so that the plasma energy will be also much higher compared with the plasma generated from picosecond. So optical breakdown, which is achieved by nanosecond pulse, can have a non-ionizing side effects, which is the photo disruption. So what they mean is, in the figure here, so when you are using picosecond, femtosecond, then most of optical breakdown is coming as a plasma formation. But in the nanosecond range, or a little bit longer than the picosecond, then the threshold of the plasma is very high. So that generated plasma is having much higher energy compared with the picosecond. So that they have an extra form of the optical breakdown can happen. So that's why the plasma-induced ablation is having shorter pulse duration time. And to have a photo disruption, you need to have a longer pulse duration time, such as the nanosecond. So a few of the free electron can initiate the previous shown avalanche growth of the free electron. And then basically that means that accumulation of the free electron and also ions. And this free electron is absorbing energy from the photon. And then that absorbed energy can be used to accelerate this free electron. So that this accelerated free electron can actually hit with another atom and then making that atom to be ionized so that you will have one more free electron. So coming in free electron plus ejected free electron, now there are two free electrons. However, you can imagine that those two free electrons will have a lower kinetic energy compared with the initial electron because they lost energy to make another electron to come out. So if you just stop at that moment, then there will be no more further increase because that two electrons from the single electron is having a lower kinetic energy. However, if they are having continued supply of the energy from the incoming photons, then they can accelerate again. And then those accelerated electrons can hit another atom. And then it will release two more electrons. So that 1 becomes 2, 2 becomes 4, and then 승령, 4 becomes 8, and then 8 becomes 16. Okay, Jihun, 16 becomes 32. Okay, and then keep going like that. So this kind of basic process of the photon energy absorption and then converting the photon energy into the acceleration of the electron, that is called as inverse Bremsstrahlung. So Bremsstrahlung is actually inverse of that. So in the Bremsstrahlung process, they are losing kinetic energy to generate some form of the radiation. But here they are absorbing energy from the radiation, which is the photon here, and then making the electron to have a higher kinetic energy. So that's why it is called as an inverse Bremsstraff rule. Which is shown in this figure. So for the ordinary Bremsstraff rule, when there is a positive ion or proton, and then if the electron is coming with some kinetic energy, which means that with some speed, and then because of the attractive force between electron and the positive, they are slowing down, and then the difference between the speed at here versus here is going to come out as a form of the photon. So having a photon energy into the electron, and then it gains extra kinetic energy by the photon to the electron. So that is the inverse Bremsstraff process. So let's talk about the why this optical breakdown is important. So it makes it possible for the energy deposition, so energy accumulation, not only in the pigmented tissue, but also in very weakly absorbing media. So Manar, can you understand what this statement means?
It means that in also the very weak absorbing media, this, I don't know, Professor.
But you can just read. So let's read this again. So try to read this sentence. You can just read.
It is rendered possible an energy deposition not only in the pigmented tissue, but also in very weakly absorbing media.
Okay.
This leads us to that induced plasma causes an increase of absorption coefficient.
So to have a kind of thermal interaction or photoablation. So let's talk about the photoablation first. So for the photoablation, Manar, the photoablation cannot happen in any laser. It happens only when you are having very short wavelength. Why is that?
I have no idea, Professor.
Okay, your very friendly roommate, Nur, can you answer the question? Why photoablation we are using short wavelength?
I think because photoablation, we need to make like dissociation for the photon, for the ions of the atom.
Very close. Yeah, but photoablation doesn't actually talk about the ionization.
No, ionization is in the plasma induced. ablation.
Right.
But in the photoablation, we speak about dissociation of the ions.
It's rather not ions, but kind of molecules or
Molecules.
atoms. So, Ji-hoon, can you add more about why we are using short wavelength of the laser for the photoablation?
Short wavelength means the least less energy. That's why we use ablation as a low energy thing. But it's
That
pretty
lower
good.
energy, short wavelength.
Yeah. It's high energy. Sorry.
Yeah, yeah.
High energy, yeah.
So it's opposite. So when you have a
Yes.
short wavelength, it has a higher energy.
Higher energy.
Right. So photoablation. So Seung-myung, can you explain about the how the tissue can be ablated by the laser in the photoablation interaction? So in the photoablation, Seung-myung, were you in the class for the last Thursday?
No, I couldn't attend.
Right, you were not there at the time. So for other students, remember about I used the examples of the lottery and then everybody wins money. And if the money is like 10,000 won, you feel like, okay, I'm just happy, but I will just buy, lunch or dinner, but stay in the class for continue your study as a master or PhD. Because you know that finishing graduate school, you will mostly have a more bright future so that you can make more money. However, if you win the lottery with maybe 1 billion won, then you feel like, oh my God, I'm just so rich now. So you don't have to study anymore. I can do anything with 1 billion won. So I would just kind of, move out from the class and then feel happy and then be free like that. So same thing here for the photoablation, that in the photoablation, we are basically assuming that the tissues are composed of the molecules, and then those molecules are binding each other by having covalent bonding. And then that covalent bonding has each energy depending on what kind of covalent bonding. So most popular one is carbon-carbon covalent bonding, and that is having about 3.6 electron voltage. So if you supply higher than that 3.6 electron voltage energy, then those two carbon will become separated because now they have a more higher energy than before. And then they will be basically dissociate each other. That's the photoablation. But that means that to do the photoablation, you need to have a high enough energy of the laser to make it happen, right? So that means that for the photoablation, you have to use the specific wavelength of the laser. However, for the plasma-induced ablation, it's not wavelength dependent. You can use any wavelength of the laser as long as you are able to generate plasma. So that's the difference between photoablation versus plasma-induced ablation. As long as you are able to generate plasma, then the plasma generation can remove tissue, regardless of what wavelength you are using. That's the difference. And also, in terms of the thermal interaction, for the thermal interaction, what's the condition to have thermal interaction is that tissue needs to observe the light energy. And then that observed light energy is going to be turning into the heat. But in that process, the first step important is the absorption of the light by the tissue. And we all know that the absorption of the light is depending on wavelength. Let's say that if you have a high content of melanin on the skin, then since melanin can absorb very strongly on the light. However, when you have a very minimum of the melanin on the skin, then it does not absorb light, right? So with the same energy, for the high contents of melanin, it will absorb the light energy and then produce the heat. But with the low melanin, if you provide same energy, but it may not be absorbed, so that it cannot generate heat. So that's basically depending on the pigments in the tissue. So this can decide whether with the same energy of the light will be causing thermal interaction or not, depending on the absorption of the light by the tissue. So to have a thermal interaction, they will be highly depending on that observer in the tissue. However, for the plasma-induced ablation, it doesn't care whether there is a pigment or not. As long as you have highly focused with a short pulse duration so that multiphoton absorption can occur in that volume, so that if it generates plasma, then it works to remove tissue, whether there is any pigments or not. So that's maybe one of the strongest point for the plasma-induced ablation. You can do the plasma-induced ablation, doesn't matter about the light absorption by the tissue, or doesn't matter about the bonding energy, or so that doesn't matter about the wavelength of the laser. So as long as you are able to generate plasma, then you can basically remove tissue. That's the strongest point for the plasma-induced ablation. So that's why it can be used for transparent tissue, such as the cornea or lens of the eye. Of course, photoablation can be also used for the cornea and lens when they are using very short wavelength. So during the process, there is no restriction of the photon energy involved. So as long as free electron can have extra kinetic energy by absorbing any amount of energy, then it can happen. So very short rise time of the free electron density of the order of the picosecond is very important. However, the light irradiance must be strong enough to cause the rapid ionization so that losses do not quench the electron avalanche, which means that this number of electron growth is going to happen, But to continue that process, you need to have a continuous supply of the photon energy coming in. Otherwise, it will be easily quenched, which means that stop processing of the stop generating free electrons. Okay, so let's continue on the next class, which I need to record and then upload for the next Tuesday. And then Thursday, the garlic, you can have a again updating your slide and then having one more presentation. And then Jeu will also have a presentation on next Thursday. So I hope, except Seung-Young, I guess you are able to go to your lab today, but all others who are in the first floor, I hope that you enjoy your stay in your dormitory. Sometimes you can go out and enjoy the fresh air too, and enjoy the nice weather. Okay, then we will see next Tuesday from the YouTube. Okay, take care and bye.
Thank you, Professor.
Thank you, Professor.
Thank you, Professor.
Okay.